Okay, my name's Bob Corson, and I have an undergraduate degree in physics and mathematics, and then a joint degree in astronomy and electrical engineering for Carnegie Mellon and University of Pittsburgh, and then a degree in mathematics from the University of Pittsburgh. And I'm going to be talking about decoherence. Now, let's see, share. Let's do Acrobat. And hopefully everybody can see this. That looks pretty good. Okay. So this is part 4, and I'm not going to go through the abstract again because it's been the same each time. Okay, so we'll do a quick introduction, we'll do a quick review of entanglement, another quick review of isolated, closed, and open systems, and then we'll go back to coherence and decoherence. We'll do a short overview of what we did last week, and since people didn't seem to know about a moment generating function, which the Wigner function is, I'll do a little bit about that. Then I'll talk about Ein selection and pointer states, and then I'll go into the interpretation of quantum mechanics called consistent histories, and there'll be a couple of digressions that are needed in order to understand it. The first will be about paradoxes and logic, and then the second one will be about coarse graining. Then we'll talk about what the rules of consistent history are, and a small part of the experimental results that show all of this actually makes sense.
Are you recording?
Pardon?
Are you recording?
Yes,
Good.
I am. Thank you. Okay, so we did the abstract. So 4 weeks ago, we described about the correspondence principle, about spaces, configuration space, and entanglement. And we've spent the last 2 weeks describing isolated systems, closed systems, open systems. Now those systems basically depend upon how much information from the environment gets into a system. And an isolated system is one that you can't actually create. It is more or less a limit. It's a Gedanken experiment. It's the kind of thing we try to create, but we can't actually do it. A simple example is if you take a look at the biggest quantum computer right now, it's run in millikelvins, that is thousands of a Kelvin of temperature. It's in a vacuum that's more than what you would get at the surface of the moon. And you can get 15 or 20 qubits to run for maybe 200 seconds before all of the environment just destroys everything working. So that's about as close as you can get to an isolated or closed system. A closed system is an isolated system that allows energy to move in and out, and usually people in a laboratory try to correct for it using theoretical computations. But no mass is allowed to go in and out of a closed system. An open system is one that just allows the environment to interact with whatever you're dealing with. Sorry?
I don't want to interrupt you. Assume that I can ask questions. May I?
Sure.
But the question is that concerning the size of the system. If you consider a single atom, say, an interstellar space, you can consider it to be a closed system. I mean, it's something like a qubit computer that has billions of atoms, and you say the size of the system affects the.
Well, you actually don't, because even an atom in the middle of space has the cosmic microwave background photons, and there are on average 400 per cubic centimeter. And that means that there's trillions of photons every second going through that atom, and they're being entangled with those photons. Now, they're not greatly entangled, but they're entangled. So you can't make a system that is isolated. Just can't do it.
I have to add that the important point here is the interaction between the photons and the atom. I mean, there are all these photons, but if the interaction cross-section is very, very, very small, then the atom is affected nicely.
Well, that's not actually the way it works. When you do any kind of a system, you'll find that they're always entangled with the environment eventually. As I said, whether it's in a quantum computer or some of the experiments I'm going to talk about, it just can't be done. So decoherence is a quantum theory that allows the interaction with open systems, the environment, and through the process of decoherence, you get the classical world that we see every day. So a quantum system is quantum when it's in a superposition of different states. And if it becomes entangled with particles in the outside world, those atoms, photons, whatever you have going on, will make records. They may not be exact records, but they'll make records of what's happening inside that system. And eventually the superposition falls away, and that's what we call decoherence. And you get a probabilistic mixture of definite states, which is what we call classical states. When the probabilities are in mixtures, that's a quantum system that's in a mixture will be classical, which you can treat it as classical. So we're going to complete now what we've been talking about with Ein selection and pointer states, and then we'll describe consistent histories, which is a way of describing quantum mechanics, or actually quantum field theory, but we'll talk about it in terms of quantum mechanics, that was started in the 70s by Gell-Mann, Hartle, who was a student of his, Robert Griffiths, who's done the famous book on particle mechanics, on omnis, and a whole host of people who have created this. And it's a method of describing quantum theory in the realm of reality. Basically, it's a way for getting what Einstein always wanted to have, and it works. So we'll finish up with at least one experiment that was done by, can't remember what Haroche's first name is, but he's a French physicist, and he got the 2012 Nobel Prize for a whole series of experiments that he did showing that decoherence gives you reality. So going back to entanglement, if you consider two separate particles, X and Y, that at the moment are not interacting with each other, as soon as they do interact with each other, they become entangled. The wave functions start out initially as separate, but when they interact, they become one quantum function, which operates in the configuration space. And that is, in quantum mechanics, that's why it's non-local. In quantum field theory, you don't have that problem, it's relativistic. Okay, so each particle, as I said, has its own wave function, predicts distribution of probabilities, and initially, while they're initially entangled, they're definitely going to have interference effects. However, eventually, and the typical way in which we think about it is, say, electrons and their spins, if they're completely entangled, then there will be a spin up and a spin down, and no matter how far away they are, they will automatically, if you know one, you know what the other one is. You don't know which one it's going to be the first time, but you know what the second one will be. Okay. So as these particles are not interacting before they're interacting, they're uncorrelated. But once they collide together, they will have some degree of entanglement. May not be completely entangled. The preparation that we do generally to get complete entanglement is a very special type of system that you have to set up. Okay, but once they have interacted, they are now correlated with each other. So if we measure as I said, if we measure a totally entangled pair, and because of the law of angular momentum of conservation, then if one is spin up, the other one has to be spin down, since the total has to be zero.
If two particles collide and become entangled.
Collide is a bad word. Interact is a better, because collision is a word you use to talk about particles, like billiard balls colliding each other. This is not about collisions. It's about fields interacting with each other.
Okay. However, they remain separate, however, but entangled.
Well, in reality, quantum mechanics doesn't work, okay? It works, quantum mechanics talks about particles, real particles. And it doesn't work because everything in the standard model of physics is based on fields. And fields have two properties: intensity and frequency. Frequency is continuous, and you take Planck's constant times the frequency, that gives you the energy. The intensity is quantized. It's got units. So you get 1, 2, 3 of these units of energy. And that is the way the field interacts. And so if you have two field excitations that are going to get close to each other, when the field gets close together, they become entangled. And you're actually using the Dirac equation, not the Schrodinger equation. I'm not going to do this all these times, but when I say Schrodinger equation, think Dirac equation. And you're talking not about particles, not about collisions, but field interactions.
Okay. So assuming you can have two systems, the ability to use this interacting, after they become entangled, one of them then interact with a third one.
Yes.
So they're constantly interacting with the next guy over.
Yep.
So is there anything that is not?
Well, what we did last week was we talked about a process that Dieter Zay initially started, and Wojciech Zurick, who's was a student under Wheeler, had developed this process where basically the interactions that you're talking about are very similar to what are called spin glasses. And it's a map that's called the Baker's map, and we did a picture of it last week that showed how they mix all things up together. And that is the process that happens, and it's a Brownian motion of these fractal trajectories of the excitations. And when you're eventually going to have, trillions, more than trillions at least, of things that are entangled, and it's going to happen very, very quickly. We did a calculation last week that showed them, I think, in less than 10 to the minus 20th seconds or something like that, to do trillions of interactions. So because as they go out, they get less and less entangled, each time you have one that's a little less entangled than the one it was before when they get entangled. So as they go out, it keeps going down, and you can, at a certain region, effectively say that it's not entangled from here on. But it's only an effective thing, and we'll talk about that in consistent histories. Okay? Any other questions?
Yeah, I have a question. So is the entanglement moving outwards at speed of light, or is it staying?
No, it depends. Well, for all of the fields that we're talking about, the excitations can, like the electron field in the Dirac equation, they can. It's a funny system. It's, again, a fractal type of trajectory. So if you look at it in detail, you've got a jagged rule. All of those pieces are going at the speed of light, but the average as you go across is going less than the speed of light. So and anytime you get a excitation that's going in a, say, a bubble chamber or something like that. They're going much slower. But it's a funny way of doing the calculations. I'm trying to be as accurate as I can. It's hard to say all of these things in really accurate kinds of ways. So anyway, isolated, closed, and open systems, we've talked about them a little bit. And basically, a thermodynamic system is one that is believed to be in an equilibrium and has a wall around it. If it's an isolated system, it means that no energy and no mass can go across the boundary. If it's a closed system, no mass can go across the boundary, but energy can. And in an open system, which is basically, eventually all systems become open systems. The boundary is essentially notional. It's, you know, it really doesn't matter. Okay, back to coherence and decoherence. The word decoherence is a physicist's invention. It also could have been called classification, but unfortunately that word was already had another meaning. By classification, I mean to make classify, to make classical. That would be the way in which you would think about it. But since it was already used for a different meaning, they couldn't use it without confusion, so they invented a word called decoherence. And to decohere means to become less and less coherent or to lose coherence. And the word coherence, we did some talk last week again about how if you take various kinds of two-particle systems and you just have exactly the same frequencies everywhere, you're going to have interference. But as you add more and more waves of different frequencies, the interference dims down. That's decoherence. If they all have the same frequency, then they're coherent and they give you interference, which is what we see in quantum mechanics or quantum theory. And decoherence is when all of these different photons of different frequencies and particles that are going through that have different energies and therefore different frequencies, different momentas, the process decoheres. It becomes less and less a single system that has direct correlations, but has a larger system with less and less interference in it.
It said you take a two-slit experiment and you set it up in a laboratory, say, to demonstrate the underground heat. It looks like pure quantum mechanics without any decoherence.
But that's because the electrons that are being sent down there are being prepared so they all have the same momentum and therefore all have the same frequency using de Broglie's rule. And thus they interfere with each other. But if you were to have a whole bunch of electrons coming at various energies and momenta, and you wouldn't get the same process.
I understand.
I think the still part is if I can just you send one electron at a time. That's where you get the interference.
But it's only if they have the same energy and momentum. If they, yeah, it doesn't matter. If you do one electron at a time with random,
They have the same. That's a macroscopic detection apparatus. That's what the decoherence. You only get the electron in one spot. You still get a bunch of probabilities, but they're all classical probabilities. If you had the electron, if you didn't have the decoherence, then somehow it would affect 2 or 3 or 100 places.
Without decoherence, you can't see what's going on.
yeah, you'll see in the pictures at the end in the experiments where they start out in what's called a Schrodinger-Cat state, and there's interference in between them. And then as the process evolves and in one of the experiments that's done, they let the system degas the container that it's in. You start out in a pressure that is less than the pressure of the moon, much less than that, 1,000 times less, I believe. And then you let it degas because it's been in a system, and as the gas gets into the system, there's very tiny, instead of 1,000th of the moon's pressure, you have 1/900th of the pressure, and the interference goes down. Then you let it do it a little longer, and it goes to an 1/800th of the moon, and it goes down more. As you keep adding any kind of either photons into the system or gas or anything, all of the interference effects go away. That's decoherence.
When you're doing that, are you basing it on like ratio between the maximum and minimum? Because you're saying they're at a certain level.
Yeah, if you take a look at the probability distribution of interference, you get a picture that looks like this. So you've got a certain maximum height here. Well, as you add more in either photons or gas or whatever you have in the system, then the heights all go down. And as it goes up, it eventually becomes.
I'm like just interested in, if you just said minimum, how low is the minimum? In other words, it's sort of showing a 0, but as you're doing this, I'm sure it's.
Yeah, there's something left, but it within, in the experiment that I'm going to show you, in 50 milliseconds, it essentially is classical.
Well, okay, here's a question. You measure the minimum and you measure the maximum. The minimum is not going to be perfect, whatever reason. I'm just wondering, is it 1,000 to 1 difference, 1,000,000 to 1, 100 to 1? And you're talking about you're getting towards experiments now.
Yeah, the experiments, first of all, there'll be a movie that shows, well, at least a picture that shows what the calculations of the exact results are and what the experimental measurements are, which are not exactly the same. And they show the pictures as you go along in time as the photons, in this particular experiment, photons are added into the system and it decoheres. Okay. So decoherence is the loss of the ability to interfere. That's basically what we're talking about. And Wojciech Zurick, as I said last week, considers this to be a quantum chaotic system. And he uses the same mapping that is used in spin glasses for distributing various kinds of magnets. And a chaotic system is one that's characterized by strong dependence on initial conditions and on perturbations. Eugene Wigner developed what he called a quasi-probability distribution to study quantum corrections from quantum systems to classical statistical mechanics. And his goal was to link the wave function that appeared in Schrodinger's equation to a probability distribution in classical phase space. And the picture here on the left is what a classical cat state is called, but this would be the same as spin up and spin down. The possibility of being dead or alive or being up or down, interfering. In 1949, Moyle re-derived it independently and recognized that it was actually a moment generating function. And we talked about this last week, but nobody seemed to know what it was, so I'm going to go a little about it in here. So suppose we want to have the first n moments of a probability distribution. If you have an infinite list of the moments of a probability distribution, it's equivalent to the probability distribution. So there are two ways of getting the same information. And I'm not going to talk about general cases. I'm going to talk about the simplest one that I can possibly think about, which is a uniform distribution over the interval -1 to 1. So that means this function is 1/2 anywhere between -1 to 1, and it's 0 anywhere else. And the moments are just the expected values of x to each power k. So that's pretty straightforward. Since it's 0 outside of -1 to 1, you can just change the limits on the integral from -1 to 1. Since the value is 1/2 in there, you can take that out. You've got x to the k. You put that in and you get this value -1 to the k plus 1 divided by 2 times k plus 1, as long as k is greater than -1. So that means the 0th moment, which is the total probability, is 1, which it always has to be. The mean is 0 because it's symmetric over -1 to 1. The variance is 1/3. The fourth moment, let's see, the third is called a skewness. The fourth is called what? Kurtosis, right. So the kurtosis here is 0. The fifth one is 1/5. I'm sorry, the fourth one is 1/5. The pardon?
I would imagine all the odd ones.
Yeah, all the odd ones vanish, and only the even one. So you get 1, 1/3, 1/5, 1/7, 1/9, etc.
Question: why isn't this the same thing as the Fourier constant? If the number is not enough to
Well, yeah, you have an e to the I omega as your.
I understand that. What I'm saying is, isn't this equivalent mathematical way of saying the same thing?
No.
Well, it is in this,
I can describe
it
this
is
function.
in the sense that if you know all the numbers, you can reconstruct it.
If I know what was defined those, I can move it.
That's where the.
But the importance in quantum mechanics is correlations, and you can do these correlations based on the moments. Anyway, what's a generating function? This is the reason we're doing this. You do the expectation of t to x, whatever probability distribution x is used in. In the case that we've been talking about here, we're talking about a uniform distribution over -1 to 1. So we take the average of e to the tx, where it is that. Again, same result. You have 1/2 integral -1 to 1, e to the tx, dx gives you sinh of t divided by t. Okay, so if you want to know, if you have a generating function, then the kth derivative of that function provides the kth moment of the probability distribution. That's the reason people are interested in them. And if you write the Taylor series of sinh t divided by t, you can see that it's got t to the k divided by k factorial times what previously was calculated as the moments. And if you take t to the k and you take the derivative, the kth derivative of t to the k, you get k factorial, so the k factorials drop out, and the coefficient, if you then take it at 0, what's left is just the kth moment. In this particular case, if you do the derivatives of sinh t over t, you get a long, complicated set of sinh and coches coming out of the derivatives divided by a polynomial in t. And so in this particular case, you have to take the limit as t goes to 0 for all those functions in order to get the right answer. But you get the same thing. Okay, so back to decoherence. The chaotic map that we showed last week, called the Baker's map, is isomorphic to the same behavior in spin glasses, a certain type of magnet. In ferromagnetic solids, the component atoms' magnetic spins all align in the same direction. Spin glasses are, in contrast with ferromagnetic magnets, are disordered magnets with atom spins not aligned in a regular pattern. And this way of disordering the entangled systems in decoherence leads to a frictional Brownian motion of the quantum system. And this process very quickly creates the entire system to be a mixture of quantum states that is classical, because they're mixtures, not entangled anymore. Or, well, they're still entangled, but essentially the interference has gone down. So in quantum theory, ion selection, which was coined by Wojciech Zurick, is short for environment-induced superselection. And it's a process that is to explain the appearance of, quote, wave function collapse, unquote. In consistent histories, there is no wave function collapse. That is, in the old quantum mechanics that was developed by von Neumann, he just, and so did Dirac actually, arbitrarily said, well, we need to know that these are various kinds of operators, and you put the operator between the wave function and the complex conjugate of the wave function, get that value, and you get what the eigenvalue will be. But the purpose of this system, the purpose of all of this work, is to show that you get classical results without using that arbitrary added axiom that von Neumann and Dirac and for many people added. So due to the interaction with the environment, the vast majority of states in Hilbert space of a quantum open system become highly unstable due to the entangling interaction with the environment. The process of line selection, in effect, monitors selected observables of the system. And after a decoherence time, which can be from 10 to the minus 20th seconds to a few milliseconds, and in the case, the longest one that I've ever heard of is the qubits, which is 200 seconds. And that's when you have about 15 or 20 of those qubits. So after a decoherence time, we give an example. We gave a example in the previous lecture of how it decays into an uncertain state, which can be decomposed into a mixture of simple, again, another name that is simply used, pointer states. What it means is, if you take a look at the probability matrix for the S matrix or the interaction matrix, typically all of the off-diagonal probabilities or correlations here exist, and that's because they're interfering with different states. When the states no longer interfere, it becomes a diagonal system. And when it's diagonal, you have a classical system, a mixture of states. And so you have just pointer states. They're stable despite the environment interaction, because they're created by the environment interaction. And the line-selected states lack coherence, and therefore they do not exhibit quantum behavior of entanglement or superposition. Zurick, Zay, and all of the folks of decoherent histories, Gelman, Hartle, Omnes, Griffiths, Docker, Kent, Elwain, list goes on and on, argue that only quasi-local, essentially classical states survive the decoherence process. Line selection can be in many ways explained as the emergence of classical reality in a fundamental quantum universe, at least to local observers. So I'm going to go into consistent histories, but I'm going to have to do a couple of
ask you just one of that to say, the decoherence, if you look at the system, it interacts You take a quantum system, which has what we can do. It interacts with the environment. You sum over all these interactions, and what you end up with is you look at the system, all the all these localities, elements, you have a density index, which is consistent.
That's close. I'll do a quick, please allow me to just let him get a quick insight into consistent histories.
But let me just make this one point. You end up with the interference, if you're looking at the system, the interference terms, or you end up with what are essentially classical probabilities.
Right.
But there's still probability.
Oh, yeah.
I mean, that's also, of course, one of the issues that you end up not with a definite probability.
Yes, but once you have any kind of an observation by, somebody looking at somebody,
Yeah.
everybody else is going to see the same thing, and every time you look at it, it's going to still look like you.
I agree, but there's still the probability aspect. And all said and done.
Yes, with a very large system, it doesn't matter. With a very small system, then the probabilities matter.
My question is, decoherence, let's imagine a very small system which is decoherent. Can you reverse it by any means?
Sorry?
Can you reverse decoherence with decoherence?
Well, no. That's the problem. That's why it's classical. If you could do that, you'd be able to undo decoherence, and you can't. Yes, and in fact, Dieter Zeh spent most of his career not on the work about how to get reality, but he was getting the arrow of time using decoherence. Okay, so, but that's a different lecture.
But if you just reverse time, you can't do that.
You should.
But if you reverse time, they're all vice versa.
Okay, let me do a slight digression into paradoxes and logic, because the logic that is used by consistent histories is different than the way we normally think about it. So the first ones that I was able to find were the 9 paradoxes of Zeno from about 2,400 years ago. And the paradoxes are quite famous, including the paradox of Achilles and the tortoise. There are many kinds of similar kinds of paradoxes. The liar's paradox. If you have a statement, my statement is false. If it's true, then it's not true. It's false. But if it's false, then it's true. So this is a problem. The barber's paradox. In a village, a male barber shaves exactly those men that do not shave themselves. Does the barber shave himself? If he does, he doesn't, and if he doesn't, he does. So that's the problem with what Cantor started out when he founded set theory, and it was used as the basis of mathematics and in particular of logic. a series of paradoxes always seem to be a problem in mathematics. The worst one was Russell's paradox. Russell's paradox says, does the set of all sets which do not contain themselves contain itself? And if it does, then it doesn't, and if it doesn't, then it does. And Frege, who was a German mathematician and logician who had spent, I don't know, 25 years or something developing a book on logic based on set theory, when he found this paradox, he told the printer, don't bother, it's all crap. So
It was referring to set theory.
well, he had logic based on set theory. And
What was crap? Set theory?
No, his word.
well, the logic that is based on set theory is the problem. Whitehead and Russell spent, I don't know, 15 years or something like that, developing an alternative way of doing logic. And from Russell and Whitehead's point of view, those paradoxes broke logic. So they created an alternative description of logic. As I said before, the prior basis of logic was set theory. Russell created the theory of types. Now, if you think about sets, sets mix up with themselves. You can do all of the Venn diagrams. But in type theory, types never mix. So they're completely independent of each other. And you can't have any things that mix. So the result was a logic that was three-valued, not two-valued. True, false, and lexically meaningless. The negation of true is false. The negation of false is true. But the negation of meaningless is meaningless. And there are three types in Russell's logic. Let's take a look at how it works at the barber's paradox. In a village, a male barber shaves exactly all men who don't shave themselves. Does the barber shave itself? Barbers are one type of men. Customers are another type of men. Types never mix, so the statement, does the barber shave itself, is meaningless. And it is this three-valued logic that is used in consistent histories, not the usual two-valued set-based logic. Okay, coarse graining. I did this, I don't know, 9 months ago or something, whenever we were doing thermodynamics, but I'll do it again. So we're going to take a deck of 4 cards, and we'll call them 1, 2, 3, 4. We won't have any suits on them, just the numbers. And if you do all possible shuffles, you're going to get 24. And I've listed the 24 shuffles. So this would be the ensemble of the shuffles of a deck of 4 cards. But suppose you don't want to deal with 24 shuffles. You only want to have instead 2 cards. So one possible way to do it is to, whenever a shuffle comes up, sum the first 3 cards in each of the shuffle, and then the other one is the second card. So if you do that, you wind up with 4 unique shuffles, 6, 4, 7, 3, 8, 2, and 9, 1, each of which has 6. So the total is 24. So you can replace the 24 ensemble with an ensemble of 4 entries: 6 and 4, 7, 3, 8, 2, 9, 1. Everything always adds to 10 in the 4-deck system, and they do here as well. So coarse graining is analogous to using thermodynamic 3-state variables like pressure, temperature, and volume for gases. This is an analogous kind of process. Let's do a second example. We're going to sum the first 2 cards in the shuffle and then the last 2 cards. So now our 24 shuffles turn out to be 3, 7, 3, 7, 4, 6, 4, 6, 5, 5, 5, etc. If you take a look at their counts, you find that 3, 7, there are 4 of them. 4, 6, there are 4. 5, 5, there's 8. And 6, 4 is 4, and 7, 3 is 4. So if you want to have an equivalent ensemble, you have to use not 5 entries, but 6. So you had 3, 7, 4, 6, 5, 5, 5, 5, 6, 4, and 7, 3. Now, if you choose randomly from this, you have an equivalent shorter deck that you started with. So there's many other ones that I could continue doing this kind of thing to show that there's nothing special about summing these up. You can put random variables, numbers on them and sum them, and you'll get different results every time you do it. So, but coarse graining is basically a way to take a large ensemble and deal with a small ensemble by making a whole bunch of equivalence classes. So we had 24, and out of those we had, in this case, 4 that were equivalent to 3, 7, 4 that were equivalent to 4, 6, 8 that were equivalent to 5, 5, 4 to 6, 4, and 4 to 7, 3. So you create equivalence classes in your system. I hope this is enough of an explanation to understand how it works. So consistent histories, also known as decoherent histories, depending upon whether you're initially Gelman or your Griffiths, but they're the same process. They were independently developed over time. Gelman first in the 70s and Griffith in the 80s. So it's an approach to generalizing the conventional Copenhagen interpretation. And the initial reason for it was because when you looked at quantum mechanics and cosmology, the Copenhagen interpretation doesn't make any sense because you need to have an observer. You can't have an observer outside the universe. So it all breaks down. So the question was, how can we get cosmology to work in quantum mechanics? So the consistent histories interpretation is based on a consistency criterion that allows probabilities to be assigned to various alternative histories of a system. So think of Feynman's path integration form of QED. You have all of these different kinds of, systems. Let me, well, I'll get to it again, but you have all of these different types of paths that you can go in the path integral form. And what you do in consistent histories is you create equivalence classes for these different paths, trajectories through the system. And there's a consistency function based on the logic of consistent histories that forces all of the paths to essentially be classical.
Does this mean that there is only one possible outcome? In Feynman's formulation, each one of these paths, you can calculate an amplitude for the event that happens. And then you have to add all the amplitudes together. And then you can conduct and calculate probability from the scale of the amplitude. You're still in the probability range.
Right, but this is still following the von Neumann structure, where you have a single Hilbert space, and you have a ray in that space, and time rotates that over time, and eventually you apply an operator, and you get a result. This is a different system. As we're going to talk about it, you split time up into units, and you use different Hilbert spaces. You do a Hilbert space from the initial position to T1 that follows the Schrodinger equation, for example, or the Dirac equation, whatever you're dealing with. Then you reinitiate based on the results that you get of this class of trajectories, and you get a certain set of probabilities. Those give you the initial conditions for Schrodinger's equation between T1 and T2. That's a different Hilbert space. Then from T2 to T3, you got a different Hilbert space. Each time you do the process, you change the Hilbert space. So the whole idea of there being a single ray that's being rotated, which is what the path integral form that you were talking about is doing, is not being done, because you have a different Hilbert space every different time as you're going through it. Okay. So, and in particular, the other main reason that they wanted to avoid was wave function collapse. And we've talked about that in decoherence here. Now, Feynman wasn't one of the people who developed this, but a couple of months before Feynman died, Gelman had a seminar at Caltech about, at that point, what he was, he'd been since the end of the 70s until basically 90, he had come through with this idea of what he called decoherent histories, not consistent histories. But anyway, he described all of this information, all this way it worked at the time. And Feynman, you know, he was in attendance all the time. At the end, he stood up, and some of the students expected to have an exciting argument. But his comment was, I agree with everything you said.
Feynman agreed with Gilman.
Yes. So he's not one of the creators, but he thought it made sense. Now, as I've said, it's based on quantum field theory, not quantum mechanics, but if you think about, again, the path integral approach, you have to consider all paths, non-local, local, first order, second order loops, everything. This would be called, in consistent histories, fine-grained histories. They're the ones that are used in Feynman diagrams and are the most refined descriptions of the universe. And but if you're actually going to deal with 10 to the 24th particles, you can't do anything with it. So an example would be a detailed time history split up of a particle that goes in either one or the other slit in a two-slit experiment. Coarse-grained histories, we've talked about coarse graining. These histories are physically meaningful partitions of the fine-grained histories. So you create equivalence classes of the paths, and you essentially average or use the usual process, but you look at it from how much interference there is in the system under these set of trajectories. And trajectories which have interference, you have to expand the system until you get to the point of where at the t to ti to ti plus 1 time you're dealing with, all of the decoherence gets rid of the interference. So you wind up having a classical path. That's what we mean by physically meaningful. You have to have a decoherence functional. Here we need a measure of interference. It's not always, but sometimes it's the Wigner function, again, that we just talked about earlier, between alternate coarse-grained histories. So now you treat with all of these equivalence classes of paths, and you use a function that tells you whether or not it's decoherent or not. And that's what Wigner function can show you, which we'll see in the experimental results.
I sort of can't relate to equivalence classes. I did the word I try to visualize the interpretations and uses.
Okay, let's
one should be one equivalence class and the other should be the other.
Here we have 24 shuffles. Okay. Now 6-4, the first one is the equivalent to 1, 2, 3, 4. The second 6-4 is 1, 3, 2, 4. The third one is 2134, and so forth. So each one of the coarse-grained ones is equivalent to a class of 6 other shuffles. That's the equivalence class. So 6-4 is the equivalence of 1, 2, 3, 4, 1, 3, 2, 4, 2, 1, 3, 4, and all the rest of the ones that there are in there. That's the way an equivalence class works. Did that make sense?
It does in terms of shuffles, the mathematical shuffles. I'm trying to make a bridge from that to the quantum mechanics. And just taking a simple example, say the two-slit experiment, then I call the photon going through slit A to be one equivalence class and through slit B to be the other.
Well, you've got photons going through. They're going through one at a time, but the field is always everywhere. It a electric field exists entirely in the universe, and it's only the excitation that's going through there. And so the paths that excitation, starting from way back here where it was emitted, before it goes to the first slit, there's a whole, in the Feynman QED formula, there's an infinite number of paths going between there and there. So you can take a few of those paths, and by using the decoherence functional, you can determine whether or not the class of paths will give you a non-interfering path. And then you can take more of them, and then you take more.
I can understand the basic results of the experiment without understanding the multiple different ways the particle can go through one slit, or it goes through the other. I can simply say these are two narrow slits, there's only one way the photon can go through one, it also goes through the other. So that gives me a simple description of what I see. Now, I'm asking if when you make the slit wider, you have to go into this consideration of the equivalence stuff.
Because you have to have enough of them that the interference goes away. You have to get a classical result. And even the way in which QED works, you don't actually do all possible paths. You know that the result is going to be around the classical result. So when you do it in QED, you only add a finite number and you choose the ones closest to the classical result. So this is very similar to that kind of an approach. You're choosing ones that are going to be very close to the classical result.
If you take the two slits and isolate it, then you're going to get what's going to be coherent. Now, the consistent histories that you're talking about, with that coming to the problem that you have if you slowly admit gas into the experiment so that photons interact as if it's commonly so that you interact, you introduce more and more gas. The quantum mechanical interference.
goes away. Yeah, that's all part of what they're doing in here.
So you're not, at this consistent history, you're not talking about a completely two stories, nothing except the two stories, the particle where you get photon out of it. We're talking about the system in which the photon interacts with particles that have been introduced. And decoherence is a concept.
Well, you can use it also for the isolated system.
What do they find?
Pardon?
Yeah, what do you get when
You essentially get very similar kinds of results to Bohm.
you get the interference pattern?
Yeah, you get the interference pattern if it's isolated, but the trajectories are pseudo-classical. I say pseudo because in Bohm there's the quantum potential, and that you're essentially your trajectories are not the classical trajectories; they're the constant probability trajectories along the wave function. But the difference is that you're doing it over time in breaks, and you do different quantum wave functions as you go along. Now, if there's no decoherence, you're essentially going to have the same Hilbert space as you move along. And so you'll get an equivalent kind of result that you do. But if there is decoherence, then the Hilbert space will change as you move from time to time.
You keep saying that the Hilbert space will change. What do you mean by that?
I mean that when you go from T1 to T2, you're going to have a certain set of probability distributions coming out of the result. The way quantum mechanics works in the Schrodinger equation is you have to get an initial distribution of probabilities in order to solve the Schrodinger equation. When you do one, and there's been some decoherence that happened, the probability that comes out at T2 is not the same as the one that there was there at T1. And you use that one as the initial condition of the Schrodinger equation. The solution of the Schrodinger equation is a Hilbert space. And so from T2 to T3, because it has a different initial condition, it has a different Hilbert space. Each time you solve the Schrodinger equation, you get a Hilbert space. Now, the way von Neumann did it, he assumed you were in an isolated system, and therefore the Hilbert space is always the same. And all that unitarity does is rotate that ray that your system goes in Hilbert space, and at the end you have to add an operator in order to get a result. But this is a different way. You work from time 1 to time 2 to time 3, and the end of each one gives you a probability distribution that becomes the initial conditions of the Schrodinger equation for the next time period. And because that distribution is different than it was at the first place, because there was decoherence, you're going to get a different Hilbert space. So you get a different Hilbert space every time you go from T1 to T2, T2 to T3, T3 to T4, etc.
I presume include PI
Yeah, I mean, you're doing the the same usual stuff that you do with QED. You're doing path integrals, but there's two things that are different. The first is your coarse graining. Second, you're assuming, you're measuring the amount of decoherence. And if there isn't any decoherence, then you might as well be back in the original system. You're not doing this system. But if there is decoherence, then the result will be different at T2. That becomes the initial conditions for Schrodinger equation from T2 to T3, gives you a different Hilbert space. So every time you move along, if there's decoherence, you're always changing the Hilbert space as you go along.
But the point has to be made that if you're doing the same future experiment, and you do it with one photon, you don't have a problem distributing at all. So you have to do the experiment many, many times over to generate the probability.
Yeah. Okay. So did the equivalence class roughly understand what's going on here? Okay.
What would choose with sections?
The same way that you do with ordinary quantum mechanics. When you start at T0, there's always a assumption about, I forget what the name is for the initial probability distribution. There's a way of thinking about it depending upon, of course, what the system is you're dealing with. If you're dealing with two spins in, spliners for Dirac equation, then the probabilities are 1/2 and -1/2. But you don't know which way. It's again the same normal way that you do it. But if you break it into times, and if there is some other photons going by or something like that interacting with the electron, then at every time you'll get a different set of probabilities for what those states are.
It will depend on the bits of the section, then with the T1, 1, 2, 3, 4, and so on. Is there any possibility that this could influence the result?
I'm sorry, I didn't hear.
Okay, when you are choosing the different T numbers, 1, 2, 3, 4, and so on, are they basically the same sections as far as, let's say, population-wise area? Or can they be different, or is there any rule?
I think you're asking the question right.
Oh.
The delta T's,
Yeah.
the difference between T on T don't shrink to zero.
Oh, okay. So then it doesn't
Take a
matter
limit,
what
you
you
take a
put
limit.
in.
Okay, so we talked about those decoherence functional, a way of measuring the degree at which the coarse-grained histories are determining the amount of interference there is. Once the level of interference is negligible, the probabilities are classical. The logic that we talked about, the only non-paradoxical operators are commuting operators. So non-commuting operators, for example, position and momentum, are defined as meaningless. So only commuting operators work in consistent histories. Sets of histories with negligible interference between all the members of a set are decohered. This is now you've gotten to the point of where the system has essentially become classical. So a recapitulation. First, there's a specification of closed or open systems at particular times by a series of events. Each event is a specification of the properties of the system through a projection operator for a Hilbert subspace representing the property. The time development is stochastic, involves many histories. That's why you're coarse graining. And you rely on either the Schrodinger or Dirac dynamics and treat the dynamics as going from event to event, rather than a foundation of a unitary evolution. Again, I've said this before. Von Neumann said you had one Hilbert space, you've got a ray in it, and it just rotates over time. And here you have a different Hilbert space at every time.
I have a question about the meaning of history. Suppose you do the two-slit experiment and you put 1,000 photons through it. You get a distribution, and you get a probability. You show the students, this is the probability. You repeat the same experiment again with another 1,000. You get the same probability. And again, you do it a third time, you get the same probability. But if people look at the pictures of where the photons arrive, they're all different. So you really have three different histories, but you're not interested in the fact that they're different.
Right, but that's why you have to coarse grain, because you're not dealing with individual electrons.
But you can see the fact that you're dealing with individual electrons still remains recorded where the electrons arrive. It's just the one picture difference from the other in the way that I'm interested. What's common to all of them is the common probability distribution. This is what you're looking for. So you find what you want and you ignore what you don't want to think about. You don't want to think about the fact that all of these pictures are really different from each performance of the experiment.
Right, but if you were doing the paths for each individual electron going through, just as in Bohm theory, you don't know in the initial conditions of the Schrodinger equation which one of the which one of the positions and probabilities in the initial condition of Schrodinger's equation did this particular electron start from. All the other, it started from one. There essentially an infinite number of possible places of probability that it could have had when it was leaving the place, and you don't know which one it was at when it did there. So when you're doing the calculation in the probability theory, you're talking about, again, all of the different possible electrons that could come out with different probabilities in the initial conditions. And the same.
You told me that I think discussing the point that if I were in position of the wavelength of the entire universe, then I would know exactly what this stuff.
Well,
I said to you, it looks like it's a violation of Bohm's interpretation, violates the uncertainty principle. And you said, well, it doesn't if you are in possession of the wave function of the entire universe.
I don't know. Anyway, do you know the answer, Steve?
But if you look at the Bohm interpretation, it looks like all of the pathways that the electrons follow are predetermined. So that if you know exactly what happened, you know which slit the photon went through. It goes either through one slit or the other, not through both. It's a traditional quantum mechanical explanation. And then I said, well, if you know this, doesn't this violate the uncertainty principle? And the answer I remember you were giving me was, well, you would know if you had put in possession of the wave function of the entire universe.
I don't recall that. I remember you using that example to, as applied to the resolution of the telescope, which then you can make it exact. somebody could talk about the resolution of given telescope.
What I was saying is I could determine where the star was with a small
Yeah.
telescope and a small number of photons if the Bowman interpretation was correct. I don't want to waste time for you.
The second part is that the time development is stochastic and involves many histories. Oh, I think I already talked about this, didn't I? Sorry. Okay. The consistency condition is imposed on the histories or families of histories, and only those that have, quote, a physical interpretation, which means they decohered, can you assign a probability. And now we'll finally get to some of the experimental results. Zurick Haroche received his 2012 Nobel Prize for a whole series of experiments that he did over, I don't know, 10, 15 years or something like that.
Give me 1 second. You are recording this stuff.
Yeah. So the particular experiment that we're going to take a look at, a state of a microsystem was encoded in a complete quantum description. The probabilities of all measurements outcomes are inferred from experimental measurements, which means you had to do it over and over and over again. And being a statistical concept, the state can't be obtained from a single realization. You have to do it over and over again. That's what I just said. Reconstructing the state of a set of trapped particles shielded from their environment is an important step for understanding the investigation of quantum to classical boundary. So he puts various photons into a Schrödinger cat state, which essentially polarization is in one direction, the other one is in the opposite direction, but you don't know which one is which in two photons. The Wigner function, the even and odd parts of the state are reconstructed based on the state preparation and on repeating measurements. And this is done partially by detuning in order to sort of do weak measurements, weak measurements. And the interferometer is used for state preparation and reconstruction. So the number of sampling points that he worked with was about 500 with 2,000. He has a ring of atoms in a Rydberg state that is used to measure the photons. And there's about 2,000 of these atoms in this. He does it 400 times in the realization. The dimension of the Hilbert space used for reconstruction is not infinite, but 11 in his measurements. It amazingly produces some pretty interesting results. nonetheless that it's only an 11 dimensional Hilbert space. So we're gonna, let's see, in one of the pictures, you're going to see several of the results, and you're going to see an inset. The inset shows the theoretical Wigner function for the system, and the results that are shown are the inferred Wigner function from the measurements. So you can compare how close the two are.
When you say theoretical, is it numerical or is it analytic?
Well, the cat state is actually a well-known, where are we back here? Ah, there.
Okay.
That's the Schrodinger cat state. And that is a closed form function for a cat state. So it's not numerical, it's an analytic solution. And you can compare the results as you take a look with his measurements. Now, yes, okay. So here is 3 of the experimental results. The initial condition, you have, this is the measured or inferred Wigner function. This is the cat state done. And you can see there's 2 objects, but there's interference between them in here. As you go through the experiment as a function of time, and this is about 50 milliseconds, you see that the shape of the Wigner function changes, and because it's decohering, the Wigner function also changes. Now, I believe this was done numerically, not analytically, with the decoherence here for these calculations. The initial state is an analytic solution, but when you add decoherence, you have to add numerical calculations. This is the inferred, this is the calculation. You can see there's still interference as you're going along through here. This, I think, is about 25 milliseconds in, and this is about 50 milliseconds. And you can see it, we assume here that it's essentially completely decohered. It's become classical mixed states. And here is the inferred state is not exactly completely decohered. There is a little bit of fuzziness here, but it's essentially a classical. In 50 milliseconds, it went to being completely decohered and becoming classical. Now let me see if I can, where am I? There. Okay, let's, share. That's what I wanted to do. Okay. So this is the movie that he did 400 in 50 milliseconds. And so essentially every 10th of a millisecond, he got a new set of results. So this is the the way it goes over time. You see at the bottom, the interference is getting weaker and weaker and weaker. And at the end, we are essentially. Now, the other thing he looks at here, this is a second movie that's going on that shows the difference between the odd and even functions of the wave function. And they essentially go away.
I'm not understanding how this relates to Schrodinger's cat if it does. Can I ask, does it? Take that diagram over there, which finally you end up with two red blobs. Is it an incorrect interpretation that one red blob is the capsule and the other one is clear? What kind of deconstrued in the illustration is that?
That's my take.
Pardon me?
Yeah, that these two independent results and the probability.
Right. There's a probability of half that it's dead and one half that it's alive. At the end, that's when the Wigner function goes into those, all of the interference parts in the middle go away, then you've just got.
That's definitely alive with it.
Right.
You don't get a superposition.
You have no superposition. There's no interference between it.
Would this result change or the speed of the decoherence change based on you had two atoms in the range, or how,
Yeah,
how that modified?
There's photons going in that are interacting with the two photons that are in the cat state, and that's why they're decoherent, as these other photons are flowing through the system that they have in there.
But what would make it go instead of decoherent 50, what would make it decoherent 100 or 5?
Well, how many? The more, if you weren't doing a few photons through here, it wouldn't. If you put trillions of photons through at the speed of light, you're going to have 10 to the minus 24th seconds. Yeah. But there's very few photons going through in this experiment. And that's why it takes 50 milliseconds. So hopefully you found a little bit about how come quantum mechanics actually produces classical physics.
Almost, I think the last slide you had was from quantum to classical boundary. So it's really a transition. It isn't a boundary.
Right.
It's
And
temporal in time. Everything transitions temporally from one state, from one kind of condition to the other. So it is a smooth transition. Even if you get very quickly, it is a transition.
yeah, it depends upon how much stuff is going around. In particular, this is another set of results. This is a different set of states that are called Fock states instead of cat states. And again, there's a demonstration here showing that the degree of between initially fully interfered or full superposition down to 20% in 60 milliseconds. in this case. So this is the picture to think about it. Suppose you're out with the sun at 5200, 5280, or whatever the temperature of the sun is when you see it, and you have my beautiful dog running around. There's trillions of photons that are interacting with, bouncing off of the dog. And those are going out, and in each region around here, the same type of decoherence process is going on. And so each observer sees the same system. This one measures not the dog, but measures the photons bouncing off of the dog. This one does these, and they're all in the environment around them. And you can, of course, cut this down into much smaller ideas, but this is the reason that everybody sees the same object, because decoherence sets up the regions, and you only see a very few number of photons through your eyes compared to the number that are in the environment.
I have a question about entanglement, picking up on what I asked earlier. I thought you had told us many lectures ago that once two, well, I'm going to use the word particles, but I understand it could be systems or whatever, are entangled.
I'm sorry, I can't hear what you're saying. So
Did you hear anything, or shall I start over?
start over, please.
I thought you told us many lectures ago that when two, either particles or systems or whatever become entangled, no matter how far apart they are in the universe, they remain entangled. However, today, you said as one of those two, for example, moves further and further away from the other, I guess the entanglement, I'm going to use the word dilution, it dilutes or becomes less entangled until it finally is so far away that it's no longer entangled.
Well, it's never no longer, but it is effectively.
Less entangled.
Yeah, it's so less small. It's so small that you can consider it to be.
But it's not a function of distance that you're implying. It's a function of the particles being entangled with other particles. That's effective.
Oh, that's
If they weren't,
interesting.
if they had a perfect vacuum, you would have two particles that they remain entangled.
Yeah, if you have perfect return boundary, which have perfect vacuum in it, and never let any photons go through, and so that it is really isolated. If that were true, then those particles would not, it would, yeah. But we're talking about dealing with 10 to the 24th gas per cubic centimeter. We're talking about 10 to the 12th photons of sun and cosmic microwave. There's all kinds of stuff. And as it interacts with these things, the particles, if the system is going here, the particle that is interacting with here is going to have here. So this one was only partially entangled with the original. And when it is interacting with one down here, that one's only partially interacting from there. So it's a little less interactive, a little less entangled, etc. We can go out.
Something that is not clear, really.
I'm sorry.
That is other particles, exerting entanglement into And that,
That's what we mean by the environment having all of these Einstein. The fact that the system interacts with some local particles in the area where it is, those particles will interact more, and et cetera, and that diffuses that the ground in motion that we're talking about.
so it's a function of environment and
Yes, absolutely.
Okay, so we're running out of time. So,
I'm done.
so I want to thank you, Bob, for and next week, Steve is going to tell us about